So today we are going to do the tutorial number 7 and which is based on the crystallography. The first problem is here. Calculate the theoretical density of aluminium. Given aluminium is FCC, face-centered cubic crystal structure. Lattice parameter is 4.05 angstrom. Atomic weight of aluminium is 26.98 gram per mole. The answer is also given, but today we will do this problem. So let's start. So these are the given data. So I'll take over to here. So generally the theoretical density of a material is given by where these quantities n is number of atoms in the unit cell. A is the atomic weight, V is the volume of the unit cell, Na is the Avogadro's number, right? And we already know this number is 6.023 into 10 to the power 20, right? So in this case, the given data are that the crystal is first, the crystal structure is FCC. Second data, atomic weight is given as 26.98 gram per mole. And then third data is the, lattice parameter is given as 4.05 angstrom, right? The lattice parameter is 4.05 angstrom. Now, see, almost everything is given. FCC, we can calculate this volume of the unit cell because the lattice parameter is given. Then A is given, Na we know, N we have to find out. So let's do that. So it's an FCC, so let's draw the structure. So that's a face-centered cubic. So let's draw it like this. So that's the back side of this cubic lattice. FCC, face centered cubic. So that's a cube, assuming that's a cube. The atoms would be sitting at the 8 corners available, and also they will be at the center of the faces. How many such faces are there? 6 different faces are there. So this is in this front face, this is in this face, if you like, this is in the top face, and this is, let's say, that is on the bottom surface, and so there will be other 2 atoms on the back, these 2 surfaces, right? So in this way you can calculate how many such effective atoms, number of atoms in the unit cell. See, one big mistake that you can do is, here as I said, there are 8 atoms at the corner, 6 atoms at the 2 surfaces. But that's not how you calculate the number of atoms in the unit cell. Why? Because these atoms are shared by the unit cell which are next to it. let's say these are the unit cell next to it, right? So this unit cell, which is on the right hand side of this unit cell, is also sharing these atoms. This atom is also shared with this unit cell and with this unit cell. And that's how what you can say is each corner atom is shared by 8 unit cells. How? Let's say, for example, this corner atom is shared by this one and this one, and so also there will be another one, another unit cell on the top, right? And then there will be another one on this top. This will also share this corner. There will be another one on this front, like this one. So in this way you can find out there are 8 unit cells which share this corner, and each and every corner is actually shared by 8 unit cells. And also, like this atom which is at the one of the face is shared by this unit cell and also this unit cell, so 2 unit cell. So that's point number 1, if you like, and this point number 2. Each face atoms are shared by 2 unit cells, adjacent unit cells. So in this way, what you can say? How many atoms are there in this unit cell? 8 corner atoms and plus 6 face atoms. But these 8 corner atoms are shared by 8 unit cells. So how much of this, let's say this corner atom is attached with this unit cell? 1 over 8 into there are 8 corner atoms, so 1 over 8 into 8 corner atoms. The face is shared by 2 unit cells. So this face, this face, this face, this face, and like 6 faces, and they are shared by 2 unit cells. So 1 atom is shared by 2. So it's like half is with this one and half of this atom is with this one. So half into 6, because 6 face atoms are there. So altogether you have 1 plus 3 is equal to 4 atoms. So total numbers of atoms that are there in this unit cell in one FCC unit cell, there are 4 atoms. So this is our N, which we will use in this formula. Now we are left to find out the volume, right? So lattice parameter is given, means this distance is given, and that is A. So if this is given, how much is the volume of this cube? That's volume V is equal to A cube, right? So that's a cube, right? So basically we are done. So now here we can use this formula to find out the theoretical density. So the theoretical density rho is equal to N is 4, A is 26.98 gram per mole, Then volume is A cube. How much is A? 4.05 angstrom. 4.05 angstrom. That's cube. And then Na. Na is 6.023 into 10 to the power 23. That's numbers of atoms per mole. Right? So ultimately you will have, that's gram per mole. So if you do the calculations, then it should come out to be 2.6, how much was the result? 9697 gram per. When you convert this angstrom into centimeter, and that's cube, so cube centimeter, cc. So that's your result for the first part. Now let's do the question number 2. The atomic radius of iron is 0.124 nanometer and iron is BCC, body centered cubic at room temperature. Find the lattice parameter of iron. So let's do this one. So here we are doing the question number 2. So the material is iron and it has a crystal structure of BCC, body centered cubic. So that means if we draw the unit cell, then it should have a cubic unit cell and 8 atoms at the 8 corners, and there is 1 atom which is at the center of this cube. So body centered cubic. So that's a BCC. Now, one thing I think you should be very clear is that whenever you draw a crystal and then you put some atoms at different positions, then they are not like this. They don't stay in this way. Rather, if properly drawn, then what you have to do is you have to draw in such a way that they touch each other. So in this case, the body-centered atom would be touching 8 of these different corners, right? So for example, if you have only a simple cubic, then what happens? And this is important to understand one of the part of this question that would come later. So let's say I have a simple cubic system and I have drawn it like this. Don't think that the atoms are like this much separation between them. No, not that. Actually, I have not drawn it properly. What I should have done is I should make these atoms to touch each other. But you see, if I do this, then the drawing becomes a little bit harder. Right? Like this. And this one would be touching both this one, this one, this one. How do I do that? Something like this. And then there is this background one, that corner at the extreme end back side corner. That atom would be touching this atom here. This would be touching this atom here. and this atom would be touching this atom here, right? So in this way, you have to imagine in your mind. So in this case, this atom and this is the simple cubic, this is the BCC. So in the simple cubic, these atoms, the corner atoms, touch each other here, here, here. But in case of BCC, because now you have an atom at the center, then these atoms actually would not touch each other. Because if they do, then this atom cannot be of the same type. This atom must be smaller. But they are all of the same type. So this atom, if it wants to be at the center, then this atom would be touching this one. So if I draw, it's like this. Oh, something wrong, right? So I have to be very careful here. So like this, and this background atom is also something like this. So these three atoms diagonally, they are touching with each other. Similarly, this atom, and this atom, this diagonal, other diagonal that you have, this diagonal, this atom here, and then the center atom, and then this atom, they must also be touching each other. Similarly, this atom, and this center atom must be touching each other. So in this way, you have to imagine the body-centered cubic system. But of course, when this is satisfied, that the center atom is touching each other, these two atoms would not touch each other. There will be some gap between them. Okay. So similarly, if you have a face-centered cubic, like what we did in the last class, in the last problem, if we have a face-centered cubic system where we have 8 atoms at the corner and we have 6 atoms at the faces. So that's the back face, that's the back face, this is this side face. Then on the top and bottom face, and then there is another one in the front face, this face. Right? So these 6 atoms are there on the face. But now you have to imagine that in each of the face, let's draw this face separately. So I'm drawing this face separately here. This is this face. Let's say A, B, C, D. And this center atom is E. So A, B, C, D, and this is E. So this is not the actual configuration. If I want to draw it correctly, then what I should do is like this, like this. Oh, this should not touch actually. So that should be something like this, and then this, and there must be one atom which is touching each other. Of course, this is not a perfect drawing. They all should be of the same size. So in this way, this diagonal, so that means this face diagonal here would have one atom at the corner, one atom at the center, and then one atom at this corner. So that's how this face diagonal looks like. So in this case, the body diagonal is containing 3 atoms, 1 at the center and 2 at the extreme. Here the face diagonal has 3 atoms, 1 at the center, 2 at the extremes. So this is face-centered cubic. And such understanding is necessary to do this actually problem. So anyway, coming back, the material is iron. And this is body-centered cubic system like this one. And also one more thing is given, which is that it has a atomic radius. The iron atom has an atomic radius of 0.124 nanometer. So let's do this. So one of the atom, such atom has an atomic radius, let's say R is 0.124 what nanometer was it? Yeah. So that's nanometer. Now, with this, what we have to find out, the lattice parameter means A, means the distance between this or this. It's the side length of this cube over which the atoms are sitting. So as I have already told you, the diagonal, this diagonal, so let's make a simpler diagram of this one. So let's draw this body centered cubic system again, fresh one. So that's your cube, and then there are these atoms sitting at the corners. Remember, this is the simpler form. They should be in such a way that they touch the center atom, which is at the center, right? So in this case, if this is A, then this diagonal, which is on this face, must be square root of 2 into A. Now, if that is the case, then this diagonal, which contains the 3 atoms, the body diagonal of this cube, is now having, this is A, because this cube side is A always. This one is square root 2A. So with these two sides given as it is, this diagonal would have length is equal to square root 3A, right? As we have discussed, this diagonal, meaning this diagonal, has 3 atoms lying one after another. So what do we have? Let's draw this diagonal here in a flat direction. So its total length is root 3A, this diagonal. And then there are 3 atoms. Touching each other. Very bad circles, huh? And these atoms have a radius r, and we have to find out this r. No, this r is given, we have to find out this A. This is twice r, and this is another r. So from here you can see 4r is equal to this total length, root 3A, for FCC. Now from here, A is equal to 4r by square root 3, and we already have r is equal to, so 4 into 0.124 nanometer divided by square root 3. Now this would give you A is equal to, let's see, 4 divided by the square root 3 multiplied by 0.124 is equal to, I have just calculated it, 2863 nanometer, or rather you can say 2.86 angstrom. So that's your result. The lattice parameter of the iron at room temperature, having the atomic radius for each of these iron atom 0.124 nanometer, would have a lattice constant of the BCC crystal structure to be 2.86 angstrom. That's your second question number. Let's do the third. What is the third? Within a cubic unit cell, show the point having coordinate half, 1, 1/3. Within a cubic unit cell, show the coordinate show the point having coordinate half, 1, 1/3. Half, 1, 1/3. This point you have to show in a cubic unit cell. So draw a cube. And then draw the origin. With your convenience, there is no compulsion how you have to draw it. So half, 1, 1/3. So in this direction, let's take y. In this direction, let's take x. In this direction, let's take z. The first coordinate is half. So you come along this direction, half. So from here to here, it's 1 lattice unit. From here to here, it's 1 lattice unit. From here to here, in 1 lattice unit. And they are all same because it's a simple cubic, right? So half, you come here. So that means this much is half. Then along y, you go 1. So you come here. And then along z, you go 1/3. So that's much is 1. And then along y, z, you go 1/3. Let's say it's here. Right. So that's it. So this is the point. So that means from here to here, we have 1/3. So then you have got your point, which is this one, this being the origin. This is your 0, 0, 0 point. So this is half, 1, 1/3. That's it. Then question number 4. Question number 4 is, draw the plane 3, 1/2 in a cubic unit cell. Let's do it. Plane 3, 1/2 in a unit cell, cubic unit cell. Draw the plane. 3, 1/2, isn't it? Yeah, 3, 1/2. So how do you do it? So to draw the 3, 1/2, one thing you have to be very clear. In this case, to draw this one, so these are called HKL, or the Miller indices of the plane, HKL. So for a plane, how do you calculate the Miller indices of a plane, HKL? By finding the intercept of the plane. And from the intercept of the plane on the 3 axes, x, y, z, and then the inverse the intercepts, and that's how you find out the HKL. For example, if this is your unit cell, cubic unit cell, let's say, and you are considering, let's say, this plane. This is your x, this is your y, and this is your z. So this plane is having an intercept on x-axis here. So that means at 1. It has, that's it, and it doesn't cut or intercept y and z axis. So x intercept is 1 y-intercept is infinity, because it doesn't, so it assuming that it intercept at the infinity, because this plane is parallel to y-axis, and also z is at infinity because it's also parallel to z. And then what you have to do is take the inverse of it. So inverse is 1 over 1, 1 over infinity, 1 over infinity. How much you got? 1, 0, 0. So this plane would be represented like 1, 0, 0. So these are called the HKL values, or the mirror indices of the plane. So similarly here we are already given the plane intercepts, HKL values. We have to find out the plane. So what you have to do is you have to walk back. So in this case we have 3, 1 bar, 2. Now whenever you have a bar, that means it's actually minus, right? So 1 over 3, 1 over 1 means minus 1, means this 1 bar, and then half. So these are the intercepts of this plane. These are the HKL values, and then you take the inverse and you find out the HKL values. Now we have to draw this plane having this intercept. So let's draw the cube. And you have to draw the plane such a way that it remains within the cube. So in y direction it's minus. So in that case we will have, if we choose, let's say we choose this x as we did earlier, this choose y, and this is your z. In that case what would happen? X intercept is 1 over 3, so you can come here, that's one intercept. Y intercept is minus 1, so in this direction it's positive, if you consider this to be your origin. In this direction positive, so minus 1 would be somewhere here on the back side, on the left hand side. So that's outside the cube. So that's why what we have to do is take our origin to be here, and then this is y, this is x, and this is z, so that we can take this intercept within this cube, right? So 1 over 3, again here 1 over 3, x intercept, y intercept is minus 1, so that's your y intercept. This much is 1 minus 1. Z intercept is half, so this is half, so this is 1. So that means now we have a plane which would be like this. So that's the plane, and this plane is this plane. This is the plane 3, 1 bar, 2. Within this unit cell having the origin here. That's your question number 4. Then let's do the question number 5. In the question number 5, draw the directions 236, 203 to 1 bar 1. Okay. Draw the directions. So now we are having directions to draw. Earlier we have drawn the plane. Directions having Miller indices or HKL values 236, 203, and then 1 bar 1. So first, direction having HKL values, HKL, HKL, HKL. So these are the, remember these are the square brackets. For the plane you have the braces or the simple first bracket, and these are the third bracket, right? So first bracket, second bracket, and third bracket, if you remember, first, second, third. Anyway, so for the plane, this is the bracket that you use, and then HKL. For the directions, this the third bracket. Okay, so 2, 3, 6. What you have to do is, in this case, to find out the plane, the direction, then first what you have to do is take the maximum one out of this. So in this case it's 6. So 2 by 6, 3 by 6, 6 by 6. Then you have 1 over 3, 1 over 2, and then 1. And you have the cube here. So there is no negative. So very safely you can assume this one to be your origin. Let's say this is the origin. This is X, this is Y, this is Z. Right. So 1/3 along X, 1/3 along X. So this much is 1/3. 1/2 along Y. So from here to here, you come by 1/2. So first you came in this direction, then you come in this direction, then you go 1 in this direction, in the Z direction. Oops. Here. So here. So this is the point on the top surface. And then to find out the direction, what you have to do is draw a vector starting from the origin to the point representing this cut along these 3 axes. Like this, that's how much you travel along different directions within the unit cell. And then the end point and the origin. That's how you draw the direction. So that's your direction 2, 3, 6. If you want to draw the 2, 0, 3 first, 3 is the bigger one. So you draw 2 by 3, 0 by 3, and 3 by 3. This is equal to, 2 by 3, 0, 1. So now if you want to draw the direction for this one, what you have to do is draw the cube first. So that's your cube. Again, there is no negative. Bar is not there for any one of these HKL values. So that's your X, Y, Z. If any one of these are bar negative, then you have to choose accordingly this origin. But now all are positive, so that's our origin. So 2/3 along the X, so somewhere here. So this much is 2/3. Then 0, you don't have to move along Y. Then 1. So from here, you go up along Z direction by an amount 1. So this is your final point. Right. And then you draw a vector starting from the origin. So let's draw the vector. So from the origin to the point. So that's your direction. This is the direction. How much was it? 2, 0, 3. Okay, and let's draw the last one. 2, 1 bar 1. So again, what you have to do is 2, 1 bar 1. That's the direction we need to draw. So what do we have to do? Take the maximum. So this is 2. So 1, 2 over 2 1 bar over 2, then 1 divided by 2. This is 1, this is half bar, this is half. So these are the, in a way, the intercept. So these are this is how much you need to move along x, y and z. Remember, now y is negative. So now you have to be careful to choose the origin. So if y is negative, then you just go and think about only the y-axis. So generally we take x along this direction. So this is our origin. This direction is positive y, this is z, this is x. So now we take from the origin, how much? 1 along x minus half along y. So from here to minus half. So here minus half along y, and then up along z direction half from here to here. Right. So this point is on this face. Remember, on this face. So now you draw a vector starting from the origin and up to this final point. So this is your direction 2, 1, 1. Why these are important? These are important to find out or to describe what are the positions of atoms within a crystal, within a unit cell of a crystal. You see, for iron, aluminium, copper, zinc, these are simple materials having only one type of atoms. But you have alloys or materials having molecular structures like Al2O3, NaCl, sodium chloride. So for those, you will see these different atoms making the molecule are sitting at different positions within the unit cells, and they become really complicated. And that's when if you want to mention which atom is residing where, then you would need this type of different complicated, HKL values for different planes, different atomic positions and so forth within the unit cells. So that's why you have to have a very clear knowledge of what different directions, planes, points within the unit cells are. So let's go and take the 6th, I think. Write down all the equivalent planes with Miller indices HKL equal to 3, 1 bar 2 respectively in a cubic unit cell. 3, 1 bar 2. So now you have plane 3, 1 bar 2. And you want to write all equivalent planes with the HKL values is equal to this. What does this mean? It means you just have to write all the combinations of this 3, 1 bar 2. So all the combinations like 3, 1 bar 2. So that's first. Then change 1 bar here and 3, 2. What else will be there? 1 bar here, then 2, 3. And then, so this is one plane, this is one plane, this is another plane. Then let's take 2 in the first position, 2 and 3, 1 bar. Then 2, 1 bar, 3. So these are the 2. Then what we can do, we can take 3, 2, 1 bar. Okay, so these are the 6 combinations that you have, 3, 1 bar, 2, right? So 3 distinct combinations. Then to find out all the equivalent ones, then what you have to do is, you have to 3 bar 1, 2. With this, you will find out 6 more, just like what we did. Then what you have to do is 3, 1, 2. So 6 more. Then what else? 3, 1 bar, 2 bar, 6 more. And 3 bar, 1, 2 bar, 6 more. And then 3 bar, 1 bar, 2 bar, 6 more. So these are the different combinations that you can have. In this way, 1, 2, 3, 4, 5, 6. So total, you'll be able to write down 36 different such planes, and these are all equivalent planes. And then all these 36 different planes can be represented simply by 2, 1 bar, 3, or you can take any one of these combinations and then put them in second bracket. Originally, what was it? 3, 1 bar, 2. So you can write 3, 1 bar, 2. They are all same. It doesn't matter. So what you have to remember is, given HKL values of a plane, then you have to write all the combinations of this HKL with bar and not bar, all including, right? So in this way you will do this exercise. Now to the last problem. This one is already actually discussed in the lecture video, which is the first part for the crystallography. At the very end, I discuss in lot detail about this problem, so I'm not discussing it in this tutorial. So please go and watch the crystallography first lecture, and I discuss this at the very end. Okay, so that would be the end of this tutorial sheet, and thank you very much. If you have any questions, put your questions as comments below. I'll try to answer them there. Thank you.